150 plus engineers engaged in the development of national level projects in the area of telecom security systems, network management systems, intelligent networks, operational support systems, access networks, and optical technology based products. Majority of these projects were completed successfully and commercially deployed in the public network. He also carried out significant research work in the Photonic Research Lab, Nice, France, and the Indo-French Science and Technology Corporation program on special optical fibers and fiber-based components for optical communication during 2007 to 2010. He was also closely involved with ITUT Geneva in study group 15 and represented India for various optical networking standard meetings. His research is in the area of optical core and access networks, fiber wireless architectures, optical signal processing, free space optical communication, and energy aware optical access networks. So now the session is over to you, sir. Yes, please.
Okay, thank you, Dr. Amit, for kind introduction. So the topic today is hybrid WDM TDM PONs, and I have gone through the lecture details of other speakers, so probably some fundamentals of PON has already been covered. So this is going to be more focused on a combination of WDM and TDM PONs. So during the lecture, you can ask any question, you can interrupt me. If Dr. Amit is there, maybe through the chat box, he may have access to the chat box, but I'm not able to see the chat box because I see the slides here. So if there are any questions, you can please interrupt me. I can clarify at that stage.
Yes,
okay.
Sir. Okay. Definitely, sir. Yeah.
Okay. So basically, just to make the overall thing look continuous, so I will spend some time on introduction to PON and why hybrid PONs are necessary, and what are the different components which are used in hybrid PONs, what are the issues we face in hybrid PONs, and then maybe some performance analysis which has been done for hybrid PON. I'll share some of the results there. And if time permits, another hybrid architecture, which is actually radio on fiber, I'll discuss ROF PONs if there is time at the end. And then what are the challenges we have before we have mass adoption of hybrid PONs. So this is the sort of flow of the presentation. So let us go to what is happening to the network. The network earlier it was divided into three parts: the core network, the metro network, and the access network. The core network basically spans about 200 kilometers or more than that, 200 kilometers. It has a lot of SDH, WDM equipments, and optical cross connect. And then there used to be a metro network within a metro. The distance could be typically 15 kilometers. Then lower order SDH, Ethernet, coarse WDM. So those were the elements which are used in metro network. And then finally you have the access network, which is actually from the central office to the subscriber or very close to the subscriber. So access network, typically the distance is 5 kilometers. And it uses DSL technology, ADSL, XDSL, VDSL. Those digital subscriber lines have different speeds. And then also places, we have started using passive optical network. The lower flavor of passive optical network, that is GPON or EPON, is not very popular in India. We have adopted GPON as a standard. So GPON is deployed in fairly good number in the country. But now what is happening, this somehow metro layer is evaporating. So we will be left with the core network and access network, because you can have a very long distance in access network. of the order of 50 kilometer using next generation PONs. So sort of, number of equipments which are there in the network, they are getting reduced. The power consumption in the network is getting reduced. The space you require in the exchange for placing those equipments, they are getting reduced. So you see, sort of core is directly interacting to the access network, thereby eliminating the metro network. So what is the effect which it will have? So today, basically with conventional networks where you have core or metro and access, you have a lot of equipments. You have core switches, you have data cross connects or voice switches, DSLAMs, digital subscriber line access multiplexers, and a lot of devices in the access network. So basically a typical scenario where you have 15,000 subscribers, it will occupy about 900 racks. I mean, these are special racks which are used for housing telecom equipment, and the power consumption is very, very high, 826. But 21st century, as these two, the metro gets removed from the overall network, we reduce to 20 racks. The space required, power consumption also drastically decreases. And then the long-term vision is that you're directly connected from the core to the access. Probably one rack solution is good enough for 15,000 subscribers and 100 watts. So you see the drastic reduction which is happening with this access technology and the advancement which has happened in the access technology. So the current access technology, if you see, they are ADSL, which uses twisted pair. The typical speed is about 15 megabit. These are all asymmetric services. Downstream is more than the upstream. So 15 and 3.5, the reach could be about 5 kilometers. VDSL, a higher version of DSL, can give you about 100 megabits downstream. The distance gets reduced because the speed is high. Twisted pair cannot, at high speed cannot cover a long distance. And the other option is use of HFC, that is hybrid fiber coax. So can get higher speed, about 40. The reach is also a little higher. But then you require that kind of infrastructure where you have, hybrid fiber coax system installed. And then Wi-Fi, which is a wireless 54 megabit. I mean, these are, commercially available and which are deployed systems, and typical distance you get is 0.1. WiMAX used to be one of the technology where you got more distance and higher speed, but not no longer used in big scale. And currently we have EPON and GPON. GPON is currently deployed in India, EPON mostly in China. So you can get 2.5 gigabit downstream and 2.5 gigabit upstream, and with 20 kilometer reach. So these are the current access technologies which are in the network. So what is the motivation? So what is the motivation of going for passive optical networks? So as you know, the traffic is increasing at a very rapid speed, and there's a lot of dependency on the internet information across the globe. So there are some statistics, every minute there are 12 million email messages moving across internet, 500,000 voicemail messages moving in a minute, and 100 million people log onto internet in a day to access various types of information. So in order to handle this information flow, neither DSL nor cable modems, when I say cable modems, it is that HFC kind of solution, can keep up with this high demand. So because these technologies, they depend on copper, and that copper is actually optimized only for voice traffic, not for data traffic. So DSL cable modems, they have some limitation in terms of supporting high data rate. And also it is not designed for telephony or video, primarily for data access network. So that is why we have now shifted. Yeah, sorry, there was some question, or there was, what was that? Okay. So passive optical network is a technology which is viewed as very attractive solution to handle this information flow, high information flow. So basically, PON allows a longer distance between the central office and the customer premises, and you can reach a distance of about 20 kilometers, as I said. So just, I'm sure earlier speakers must have discussed in detail about the basic overview of PON, but just a couple of minutes I'll take. So basically, it has got three units. One is OLT, optical line terminator, which is in the central office and interfaces with the network, with the ISP operators, with the video provider, and then you have a fiber going to a point where you split the fiber into, would be 16 parts or 64 or 254 depending upon the application, and this particular device which splits is actually a passive device. You don't require any power here. That is why you call this as a passive optical network. You require power only at the OLT and at the remote unit, not in between, in between OLT and ONU. And then you have, ONU, optical network unit, connected to the distribution fibers, and from ONU, depending upon the location, this ONU, it could be in the office building, or it can be in the curbside, or it can be a little away from the house. So all flavors of fiber to the X are covered under this architecture: fiber to the curb, or fiber to the building, or fiber to the home. And the traffic which flows from OLT to ONU is downstream traffic, and the traffic which flows from ONU to OLT is upstream traffic. So this is the basic architecture of passive optical network. What are the advantages? I mean, you can have high line rate because the capacity of the fiber is quite high, so you can handle high data rate, high line rate, and you can cover a longer physical reach. So there are long range PONs also, which can cover much more than 20 kilometers. But a typical PON covers a distance of 20 kilometers without any amplification. Long reach PON might require some amplification in between. And this is achieved because the fiber which you use has got very, very low attenuation of the order of 0.3 dB per kilometer. And the central office equipment is actually shared among all the users. So electro-optic component and electrical devices, they are all shared among large number of subscribers. And there is a reduced maintenance cost, as we don't require any electrical power in the field, because the splitter which you are using in the field is passive in nature, which does not require any power. So these are some of the advantages of passive optical network. What is the current status of PON? So downstream, the traffic OLT sends data. So it is a TDM kind of flow which is going from OLT to ONU. So there is no collision happening there. In upstream traffic, ONUs can send data. So because any ONU can transmit data, so we need to have some mechanism in place to avoid that collision. Ethernet offers CSMA CD. This is for EPON. So there are several types of multiplexing scheme which is possible when you transmit data from OLT to ONU. So time division multiplex is the common standard for PON, but there are systems where you have WDM, you have different wavelengths, each carrying some different data rate. They are multiplexed optically and then transmit over the PON infrastructure. So those are WDM. And the third category could be a combination of these two. So we will understand what is the problem with TDM, what is the problem with WDM, and how such problems are resolved in hybrid WDM TDM. That is the discussion topic today. Just hello, is there any question there? Yeah, so if
yes,
you're...
no, sir, there is no question right now.
Okay, I think somebody has unmuted. So
Yes.
anyway, so please, people who are not asking any question can mute. And if you're asking a question, then unmute and ask. Okay, thanks. So comparison between EPON, GPON, just very brief. I'm sure in detail earlier speakers must have covered. So EPON is the standards are mainly from IEEE. And GPON, the standards are from ITUT, International Telecommunication Union transmission. And EPON can give you downstream and upstream 1.2 gigabit per second, the conventional EPON. There is progress happening in EPON as well. And GPON, the conventional, can give you 2.4, and the other side would be either 1.2 gigabit or 2.4 gigabit. It could be symmetric. Split ratio, conventional EPON supports up to 60, GPON can support 64. The line coding, that is from the OLT to the ONU, the line coding is used 8-bit to 10 bits, so which actually increases the bit rate. And whereas in GPON it is non-return to 0, it's scrambled NRZ, so there is no increase in data rate. Protocol which is used in EPON is Ethernet, native Ethernet, and GPON it is combination of ATM and TDM. And since EPON is primarily for data traffic, so quality of service is not supported. It goes by best effort. Security is again not guaranteed, whereas GPON supports quality of service. There is quality of service for video. There is a quality of service parameter defined for data traffic, and it also supports advanced equipment security features, AES. And then also, in order to improve the performance of the system, it uses some forward error correction code, which is actually not mandatory. It is an optional feature, and the recommendation is to use Reed-Solomon code 255-239. So these are the basic difference between these two technologies. And if I show you what is the multiplexing technique involved, let me use the pointer here. Just 1 second. Should be okay. Yeah. So this is TDM-PON, where you have this data which is shown as, these are packets shown as 1, 2, 3. So all the composite data which are for all the ONUs, they travel through this network. And ONU, depending upon which packet is meant for that particular ONU, is processed by that ONU, and you get the relevant data which is useful to the ONU1, for example, here, the green packet, and similarly for others. So this is the basic concept of TDM-PON. And in WDM-PON, what happens? You have many wavelengths in the fiber, lambda 1 to lambda n, and each lambda carries a different traffic. It's transparent to traffic. It could be any speed. It could be even analog signal or digital signal. So, and these different wavelengths, they are all multiplexed, and these multiplexed wavelength, the summation or all the wavelengths will travel from splitter to the ONT, and depending upon if you configure your system, say lambda 1 for this house, then it'll have corresponding filter. It can remove the information from lambda 1, and this is how the information is available to this particular user. Similarly, for lambda 2 or lambda n. So this is a basic principle of WDM-PON. In the hybrid PON, actually, you have a combination of TDM-PON and WDM-PON. So what happens here? You might have, TDM-PON, for example, say 4 TDM-PONs, each with lambda 1. And within that lambda 1, it is only a TDM-PON. And then you can have, 4 or 8 such lambdas. And they're all multiplexed. And then through a wavelength division multiplexer, the information flows. And then you can, have WDM demultiplexer, wherein you demultiplex from lambda 1 lambda 8, and then from that lambda 1, the usual PON will take over. So it is basically a combination of WDM technology as well as TDM-PON technology. And we will see that, this has much better result as compared to, other two variants. So TDM-PON, basically remote node containing optical power splitters connect to many venues, as I have explained, and there's a splitter in between. And at ONU, the relevant packet with correct address label is processed and all other data is discarded. So this is a repetition of what I said. PON, problem with PON is that there's a shared traffic structure. That's a major roadblock for the future development of TDM, because I need to multiplex all kind of traffic into TDM. Only then I can transport. So this could be a problem. And furthermore, the splitter, anyway, you're using a splitter at various other places also, but there are some security concerns. And there is a good amount of power loss which happens in a splitter which is used in TDM-PON. So for example, if you want to have a 1:32 splitting, then the loss in the device is of the order of 17 dB. So in order to meet these laws, you have to increase your transmit power, or you have to improve your receiver sensitivity, because the budget available between power budget available is limited. So 70 dB insertion loss by splitter is quite high, and as the splitting ratio increases, goes to 164, the 70 will become 20, so on and so forth. So this is a sort of high splitting loss in a typical TDM network. Yeah, once again, I request to please mute. Yeah, so WDM-PON is another alternative, is a promising solution to improve the performance. I mean, you can have high bandwidth, security could be high, because if you want to tap into that information, you should have that, that kind of filter design. Only then you will be able to tap that lambda 1 or lambda 2 or whatever. And the devices which are used, which are typically AWG, I'll discuss some of these devices a little later. The loss of these devices, which I refer this as the AWG or arrayed waveguide, the loss is quite less as compared to normal splitter. And signals are coded on a separate wavelength. So, for example, lambda 1 can carry only video information, or lambda 2 can carry any specific kind of information. Lambda 3 can carry some 10 gigabit of information. Lambda 4 can carry 2 megabit. So you can have variety of information. It is transparent to the format. So that is the advantage you have in WDM-PON. So as I mentioned, the insertion loss in the splitter is much less, 3 to 5 dB, which is because of AWG. So basically, it will improve your overall power budget. And once the power budget increases, you are able to increase the transmission distance. You are able to cover a longer distance. And you are able to create a point-to-point link where a dedicated wavelength is reserved between OLT and OLT. So you can have any type of wavelengths, any type of requirement can be met by the users. The issues or the disadvantage with such a technology is that you require a receiver, because information is on lambda 1, so you require a particular receiver or transmitter which operates at lambda 1. So if there are, say, 8 or 32 such wavelengths, then one should have those 32 transmitter and receiver pairs. So it requires huge inventory for the operator. And AWG is at the moment expensive as compared to splitters, so there's a cost issue involved here. So this is hybrid WDM-PON. So PON combining WDM and TDM technologies is called hybrid PON, and is the most promising candidate for next generation optical access network. Now, the deployment which is happening is actually HPON, that is hybrid PON. It can offer high split ratio, large number of users can be connected, which are provided by TDM-PON, and you can have large number of wavelengths, that is high capacity per wavelength, which is provided by WDM-PON. So it offers both. The number of users also increase, and the data rate, the capacity of the network also increases. So it gives you both the advantages in terms of users and in terms of capacity. These are the standards, how these standards are developing. So again, as I said, there is IEEE and there is I2T. And India, we follow I2T, and I2T basically gets input from FSAN. FSAN is Full Service Access Network. It's a consortium of 70 institutions who work on this, work on access technology, and they give recommendation to ITU for making standards. So FSAN work and ITU work, they go side by side. So the standards, the standard GPON is G984, which is 2.488 gigabits per second and 1.244 gigabit upstream. This is the standard which is deployed in large number in the country. And then you have XG-PON1, which is actually 10 megabit downstream and 2.4 gigabit upstream. So this is G987, and it is not compatible with GPON, but it can coexist with GPON. Okay, and then you have a symmetric next generation XGS-PON, which is 9807.1. It has 10 gigabit both sides. So this is XGS, next generation symmetric PON, 10 gigabit on both sides. But because nowadays, earlier there used to be information flow more from upstream, that is from OLT to ONU, and ONU to OLT, the information flow used to be less. So, initial days of PON, they were unsymmetric or asymmetric PONs, asymmetric data rates. But nowadays, the information flow or file sharing or video sharing is symmetrical in both the directions. That is why ITU-T or FSAN have recommended that we should have passive optical network, which is symmetric in nature. That is having same data rate in upstream as well as downstream. Next generation PON2 is again not backward compatible with earlier versions, and is basically has TWDM-PON, which is time and wavelength division multiplex optical network. So T stands for time, wavelength, division multiplexing networks. So currently we have specifications for 4 and 8 wavelengths. So that is the current specification, which are actually frozen, and equipment, the manufacturers can make their equipments around these specifications. IEEE on the other side, they started with 1 gigabit symmetrical, and then now they have gone to 10 gigabit and 1 gigabit, 10 gigabit downstream and 1 gigabit upstream, and then 10 gigabit symmetrical. So they are also following, same path. And also there's a group which works on 100 gigabit EPON. And some of the standards which are available for IEEE is 1 gigabit and 10 gigabit, 40 gigabit is under development. So IEEE and GTU and I2T both are going parallel in terms of data rate, but Europe or US or India, they generally follow GPON, but there's a lot of deployment of EPON in China and some other countries. So this is a comparison of all the passive networks so far. So I will not go into the history of PON. Again, I'm sure earlier speakers must have done some justice to it. So we started with ATM PON and broadband PON, and then GPON. To GPON, the story is very much clear. Then you have next generation PONs and next generation PON 2, which is actually TWDM, a combination of time and wavelength division multiplexing. And you can see these are the line codes. Basically, it follows NRZ on-off keying in all the variants. Traffic mode in GPON is GPON encapsulated method. A new method has been developed for next generation XGEM or XGEM for NG-PON2. And these are the transmission medium or the optical fiber specifications where these, where the optical fiber which will be used in the network for the corresponding PONs. And these are the wavelength range for a PON, because if you are having, coexistence of some of these technologies, you have to ensure that they are on a different wavelength range. Otherwise, there will be some interference. So these are wavelength range defined for different passive optical networks for downstream as well as upstream. The speeds are defined here. So next generation PON, as said, is actually exact value is 9.953 gigabits, but generally it is referred as 10 megabits per second. And transmission speed upside is again 10 gigabits per second. The split ratio can vary, and NG-PON can have as high as 1:256 splitting ratio. So this is the development of PON family of products. So what is happening now? So we understand up to NG-PON2, by 2015, the standards are more or less finalized. It has multi-lambda, 4 or 8. And earlier it was next generation PON and next generation PON symmetric, G-PON. Now, if you want to have more flexibility, want to increase more data rate, or increase the capacity, increase the reach, and these are the enhancements which are being done. So now the trend or industry trend of the technology that we have, a lot of 5G, a lot of Internet of Things, and they are getting converged. So you're looking for still higher speed. So we have the FSAN, that is full service access network, has started working on high speed PONs, or we call it NG-PON2 plus or XG single wavelength PON plus, where system will carry much more than 10 gigabit, and preliminary specifications for 50 gigabit PON is out. And then the roadmap is that we will use some other disruptive technology for future optical access systems. So right now the things are in progress for 50 gigabit PON. We will discuss some more detail about that 50 megabit PON. So let us come back to our TWDM-PON. So this is slightly detailed architecture of TWDM-PON. So the basic architecture remains the same. That is the OLT, and then you have the fiber or the optical distribution unit, ODN, and then you have the optical network unit. So let us see, for example, these are next generation PON2 port 1, which carries traffic at lambda 1. This is at lambda 2, lambda 3, lambda 4. So you can have up to lambda 8. TWDM is currently defined by 4 and 8. So here I have shown an example of 4 wavelength TWDM-PON. So these lambda ones, which actually is a TDM-PON in itself, which is carrying 10 gigabit. So this lambda 1 is a TDM-PON. So these are actually 4 TDM-PONs, 10 gigabit symmetric. And then these 4 wavelengths, they are multiplexed. So this is the WDM part happening here. And since you want to cover a longer distance, so you need to amplify the signal. So this is some sort of booster amplifier. And this is amplified. And then all the wavelengths, they travel inside in the optical distribution network, which is the distribution fiber. And the fiber here is G652, and it can cover a distance up to 40 kilometers. And from splitter, then you have immediately you have the WDM. So you separate out lambda 1 using some tunable filter, and then this lambda 1 is actually through a receiver or pin or APD goes to a low pass filter or the optical network unit. The same thing happens for other wavelengths, and this is for the downstream. And similarly, in the upstream, you have the device laser driver, some tunable transmitter, because you are using some 4 wavelengths. So tunable transmitter is recommended. Again, I'll discuss what is the technology behind this tunable transmitter. And then it is multiplexed, and then similarly it is multiplexed from other ONUs, and the information goes through the fiber to the DEMUX. And before the DEMUX, there is because the signal level is quite low here because of long distance and additional optical components in between, which are actually have high insertion loss. So you sort of use preamplifier. And this is all ATFA-based amplifiers, erbium broad fiber amplifiers, because the wavelength is around 1500 nanometers, where ATFA work. And then you DEMUX, and then you get back your normal TDM-PON coming out from this NG-PON. So this is how a combination of TDM-PON and WDM-PON, which is referred as TWDM-PON. So this is a case of 4-wavelength TWDM-PON. So let us see what are these components. I mean, I'm using a lot of components here: tunable receiver, or tunable transmitter, or wavelength division multiplexer. So what are the components which are used in hybrid PONs? Because it involves both WDM components as well as TDM components. Or WDM components, because it is not very high count of wavelengths, it's 4 and 8. So the challenge is not that much as compared to in a dense WDM system or a ultra dense WDM system. So some of the components, let me explain. The key components could be passive components or active components. Passive component is wavelength selective filters, could be some wavelength selective couplers. Active are tunable optical filter, because you have 4 wavelengths. You want to tune as per your requirement. So there is some tunable optical filter. Tunable source, again, there are 4 wavelengths or 8 wavelengths. You should be able to tune to any of the wavelengths. And you require optical amplifier to take care of the losses. And if you want to have a long reach for TWDM-PON, so use of optical amplifier. So these are the components which are used in hybrid PONs. So I'll just explain one of the technology or one of the type of component which is used in for making some of these components which I have described here. And this is a very powerful component which is called as fiber Bragg grating. So this was actually invented in CRC, Canada, and it has n number of applications, many applications. You can use fiber Bragg grating for filtering. You can compensate your dispersion. It can be used for optical sensing. You can use for for amplifier gain flattening, because erbium broad fiber amplifier, it does not have a flat gain over the band of interest. So if you want to make the gain flatten across the wavelength or the range of 30 or 40 nanometers, then one can use this fiber Bragg grating there for making the gain curve flat. And single mode lasers, and there are a number of applications. So I'll just explain what is a fiber Bragg grating and how this Bragg grating can be used for making these components. So fiber Bragg grating, actually, it is basically in the fiber. In the fiber, you have a periodic perturbation of the fiber core. I mean, this is normal germanium fiber core, but by having some ultraviolet exposure to this area, you create some sort of perturbations. So actually the refractive index will change. And these perturbations are of sinusoidal type. And the spacing between 2 adjacent slits is called as the pitch. So this lambda is the pitch. And for creating this particular lambda, you have to use ultraviolet of this particular wavelength to give you some particular value of lambda, which plays a very important role in one of these in the applications of fiber Bragg grating. So basic fiber Bragg grating is a in-fiber passive. It is inside the fiber. This is sort of, you can call it optical band reject filter. It will be clear why it is a band reject filter shortly. And you have to imprint a periodic perturbation in the fiber core. So once I have the high intensity of ultraviolet, it will change the fiber core, refractive index, and it becomes a function of Z, and it's a periodic function of Z, because you see it's a periodic structure here. And it can be represented as n core plus delta n, which is peak refractive index, into 1 plus cos 2 pi z lambda, where lambda is a pitch of the grating. It's defined, lambda is defined as a pitch of the grating, which is achieved by exposing it to that particular lambda UV or ultraviolet. So what happens actually in such a structure, if you have many wavelengths traveling inside the fiber, the perturbation is such, or the lambda or the grating period is such that one of the wavelength gets reflected back, and other wavelengths they're allowed to pass. So sort of what you have achieved here, there were many wavelengths which are incident on this fiber Bragg grating, and one of the wavelength, depending upon the pitch of the grating period, gets reflected. So you're able to get one wavelength from all combination of wavelengths. So somehow you have achieved, filtering mechanism. So this is the fundamental principle. Based on the grating period, that particular wavelength is reflected. So if I change the grating period, some other particular wavelength will get reflected back, so on and so forth. So I can have this series of perturbations or series of such exposures inside the optical fiber, and accordingly I can get lambda 1 reflected back, lambda 2 reflected back, lambda 3 reflected back, and others will pass through. So this is the basic principle of fiber Bragg grating. So how do I achieve de-multiplexing, for example? So suppose these are 4 wavelengths which are falling onto the circulator, and what happens through the port 2, this is a fiber grating. So this is tuned to, say, lambda 2. So lambda 2 will get reflected back, and it is a dropped wavelength. And all other ones, lambda 2, lambda 3, 4 will pass. Then again you use a grating where it is tuned to, say, lambda 4. You drop lambda 4. So this way you are able to demultiplex all the wavelengths. And the reflected wavelength is called as lambda Bragg, which is given by 2, that is a pitch, grating pitch, into an effective. And the amount of power which gets reflected is given by 10 hyperbolic square kappa L. Kappa is the propagation constant, and L is the length of the grating. So just a simple concept, I am able to use this as a demultiplexing function. So this is, in typical PON network, you have so many wavelengths, and this is the grating. And then, that grating is such that you are able to drop only 1552. So this is how, you can drop a particular wavelength. Another use could be in tunable optical filters. Again, in TWDM, there are 4 wavelengths. So sometimes you have to tune to lambda 1 or lambda 2, depending upon the user, ONU or user. So you have, a lot of optical and many input frequencies, and this is tunable optical filter. It could be a thermal or it could be electrical. So there is some tuning control, and you are able to get that selected optical output frequency. So this also can be, there's the technologies available which can be used for optical filters, or to have tunability in optical filters. And this is a typical requirement of a tunable optical filter. There I require a tuning range of 200 nanometers. That means I should be able to tune it in a range of 200 nanometers, which actually corresponds to 25 gigahertz. And it will cover both, from 1330 nanometer to 1550. Because in the PON, if you see, upstream and downstream, they may come on a different window, 13 or 15. And if you have a filter which can be used both for upstream and downstream, so you require a tuning range as high as 200 nanometers. With EDFA, if you're using amplifiers, then your EDFA bandwidth is limited to 35 nanometer, where it has a flat gain. So there the tuning requirement may be 35. And also how closely you can tune. I mean, what is the separation between the channels? You know, if the channel separation is 100 gigahertz, it is a lot easier. But if it is 50 gigahertz or 25 gigahertz, which is actually less than a nanometer, then sometimes this tuning becomes a challenge. So if the distance between two successive channels is high, then tuning is easier. The technology support it. Because when you are tuning the close by channels, the crosstalk might increase. So there are specifications that the crosstalk has to be some 30 dB or better. So accordingly, you have to have the tuning. So the number of channels which you can have is actually divided by the total tuning range divided by the channel spacing, which roughly gives you the number of channels you can tune to. And tuning speed also depends how fast you can tune. So there are, you know, type 1 tuning, or class 1 rather, class 2, class 3. And this value actually depends on the application. And typical value is few milliseconds for a class 1, you know, tuning speed, which is considered as, you know, a good tuning speed. So tunable filters, actually, they are based on some interferometric technique, which is an example is Mach Zehnder interferometer or MZI. So what you do, there are two arms in MZI, and either you change the length of one arm or you change the refractive index in that arm by some control mechanism. So one of these techniques, you sort of create a phase difference between the two arms, and there can be, you know, destructive or constructive phase at the output, and accordingly you can, you know, tailor your devices. So with these parameters change, phase of the propagating light wave changes, hence the intensity of the added signal change as a function of wavelength, and you can achieve some, you know, wavelength selectivity. So there are a lot of devices which are based on interferometric principle, and MZI is the main component which is used. So Mach Zehnder Modulator, here you see, you know, there's a power in here, and these are the two electrodes. And these are the two arms of the MZI, MZM, or Mach Zehnder interferometer. And you basically either change the length of this arm, or through some means you change the refractive index of this arm. Accordingly, you will create some phase difference between the arms. You can, you know, maneuver your right. So this is just a little mathematics of MZI. So this is your output, which is coming from the Mach Zehnder modulator. And E02, if you do some mathematics, is of this form. And if you see the power output, which is this is a transfer function, this is the input power, it is actually depends on cos squared delta phi, where delta phi is the phase difference between the two arms. So if, you know, by changing this phase difference, you can have, you know, accordingly you can change your P out. So the limiting case could be 0 or 1. So either you get nothing at the output or you get 1, or if you want to make a 50-50%, then you have to have the phase difference accordingly, so that the outputs in the output arm, you know, is divided. You know, you can manipulate the way you want by changing this phase difference. Another technique which is used for WDM multiplexer or de-multiplexer is thin film filter, which is called as TFF. You see the timing because I need to. Yeah, so this is 1051. Okay. Oh, so this is a thermal. A thermal means, you know, the performance of this filter does not depend on temperature. So that is why it is called a thermal. So in this, what you have is, you know, multi-layer interface filter. And this many wavelengths or multi-wavelength light is falling onto this multi-layer interference filter, and you know, first layer will reflect one of the wavelengths. The material is such that it reflects only one. The other layer in this will reflect the other one, and so on and so forth. So you are able to achieve, you know, de-multiplexer or mux operation other way around, because these are all bidirectional devices. So you can have mux or DEMUX using thin film filter, and these are independent of temperature change. They don't vary with change. But if you have large number of ports, these devices are good for TWDM applications where you have only 4 or 8 wavelengths. But for WDM, probably these devices may not be that effective, because once you go to 32, the amount of light which is reflected is highly attenuated, which may not be useful for you. So for a limited number of ports, this device is quite useful, and TWDM, this device is quite handy there. The other thing which is quite sophisticated, which is also used in TWDM and being increasingly used in DWDMs, is arrayed waveguides. Again, actually, it is a fiber structure, and again, it depends, as I had explained, Mach Zehnder. So you have different fibers, and you somehow create the effective length different, either by changing the refractive index or physically having different length, and thereby creating phase difference, and you are able to demultiplex all the wavelengths. And this device can work in a reciprocal direction also, where you have all lambda 1 to lambda n coming here, and they will get multiplexed into a one composite signal. And these are actually dependent on temperature. So as this graph shows, with the change in temperature, there's a wavelength shift. So this wavelength shift has to be arrested, and there are specifications that in this operation you should not have wavelength shift more than 30 parts per million at some particular wavelength. So it has to be contained within that, whereas you see there's a good amount of wavelength shift happening as the temperature is changing from -40 to high temperature. So normally you use some passive compensation technique to handle that and to ensure that your shift is contained within those ITU limits of +30 parts million and between +30 and -30. So this is the result you see after compensating. So with change in temperature, there is no wavelength shift. So you get about 0.3 parts per million per degree centigrade, and if you don't use this compensation, then in a typical AWG it is about 11 parts per million per degree centigrade. So this is a sort of challenge for making these devices athermal, which does not change with temperature. Then you have wavelength tunable lasers. So there can be one option. Other option would be you have lambda 1, lambda 2, or lambda 8, all those lasers available. So you have to keep a inventory of all the lasers at one place, because if some laser goes down, you have to replace with particular wavelength. But wherein if you have a tunable laser, you don't have to keep inventory. You will have to keep only that particular laser, and you can tune as per your requirement. So that is why in field or in operation, tunable laser is very, very important. So again, the principle basically depends on the grating filters in the lasing cavity. The wavelength tuning is by either changing the. Again, I'm requesting to mute, please. You have control from there, or participants have? Okay, thanks. So yeah, so wavelength is tuned. Either you change the temperature of the grating, because once you change the temperature of the grating, that grating period changes. So you are able to change the wavelength because the grating pitch has changed. The light will get reflected from the grating pitch has changed. So some sort of tunability you can achieve, or you can change the injection current into the passive section of the grating filter. That also can help you in achieving tunability. So this is a tunable characteristic. These are different wavelengths you can tune to. So typical range is about 10 to 15 nanometer, which is not very high, and the channel spacing has to be at least 10 times the channel width. This is the channel width. So it has to be, this is spacing, has to be typically 10 times. Only then there will not be interference from the adjacent frequencies or wavelengths. The crosstalk or interference will be less if you have channel spacing 10 times the channel width. This is a tunable LED. Looks like there is a grating and there is an electrode, and through this electrode you change the parameter of this grating and you achieve some sort of tunability. You use polymer material which have got good thermal coefficient. So you can change the temperature or inject current to get that tunability. So this is an example of injection current tunability. So this is the electrical injection current you are changing, and you are getting tuned to these particular wavelengths. For example, at 40, you get this wavelength, at 60, you get this wavelength. And these are the, tuning the different wavelengths which you can tune to. So basically, you can roughly get about 30 nanometer. Within 30 nanometer, you can achieve tunability. So nowadays, the trend is to have a colorless ONU. When I say colorless ONU, that means I have a ONU. It does not depend on any lambda. So it is very generic. So I can tune to any other lambdas, whether it is for upstream traffic or downstream traffic. So that is why it is referred as colorless ONU. So there's no specific color assigned to ONU, or there is no specific lambda one assigned to ONU. So colorless ONU will support all wavelengths. So it will actually reduce the cost because you have to produce only one type of component. So there will be a volume production, and you can achieve tunable transmitter and receiver at ONU. And tunable filter is used to select or tune to any other downstream wavelengths, and tunable laser is used to provide colorless upstream transmitter. So you have both colorless transmitter. You can tune to particular wavelength, and also you have receiver which has actually that filter, tunable filter in between, and you can receive and you can tune to one particular wavelength. So you can have both colorless transmitters and colorless receivers, or in other words, colorless transceivers. This is, I hope you are able to see, this is just a better representation of colorless ONU. So let me explain here. For example, this is upstream, for example. So upstream you have all the wavelengths coming, and you have one wave filter logged. For example, this particular filter, the output will be corresponding to that particular wavelength. Similarly, in the upstream, you have all the wavelengths available. You have a filter here, gets logged to some wavelength, and then you get output at that particular wavelength. So this is just another representation of showing a colorless optical network unit or colorless optical network termination unit. How do you modulate your transmitter before multiplexing? So there are two techniques. One is either you directly modulate the laser. These are called as DML, directly modulated laser. I mean, you directly modulate the laser, and suppose there are n lasers in a TWDM, there may be 8 lasers. So each of the lasers can be modulated differently, and it's a direct modulation. So when the speed is not very high, you go for direct modulation laser DML technique. So this is a typical device. It has the DML array. You can see this laser array. It has that arrayed waveguide here, shown here in this picture. And these are some electrical contacts through which you have to modulate your laser. So this whole is, can be realized in a common substrate type of form where all these functions can be in a chip form. So whether it is, laser, or it is AWG, or, electrical modulation contacts. So they all can be realized in a particular so-called chip or optical component. But I mean, this can work directly modulated laser, maybe 2.5, and also probably might work for 10 gigabit. There'll be some issues if you modulate directly at 10 gigabit. So if you want to modulate high speed, then one has to go for externally modulated laser array, EML. So here you have a tunable laser source, which I had explained a little earlier. You tune to some lambda 1, and then this is some sort of external modulator. So this gives you actually continuous wave. It is a CW source, right? You're not directly modulating the laser. So this CW information passes through a modulator. This could be a MZI, a Mach Zehnder interferometer, where you have electrical signal, which is actually the input data. So, and which you can modulate at high speed. So, for example, if you want to have 10 gigabit or higher or 20 gigabit, then external modulation is the solution, because direct modulation of laser at that high speed is pretty difficult. So you resort to externally modulated array. So this is an example of externally modulated array. So again, this is a device which has all these components: tunable laser, it has modulator, it'll have, you know, semiconductor or optical amplifier if you want to amplify the signal. So all these things are part of the device. And now silicon photonics, you know, can enable us to integrate all these kind of devices. So another option is you generate a COM. COM meaning you generate a set of frequencies, equally spaced set of frequencies. Again, there are techniques for generating these COM. And once you generated these sequence of frequencies, you de-multiplex, so you get lambda 1 to lambda 1. And then either you can have a direct modulated laser or you can have a externally modulated laser. This is how your modulator 1 or modulator n can be configured, and then you sort of multiplexer and transmit. So again, you can, you know, integrate all these devices, the COM generation or the demultiplexers, or whether it's a DML or XML or optical amplifiers, or not optical amplifiers, but semiconductor optical amplifiers, SOAs or multiplexers. So all these can be, you know, integrated into a chip. So they are no longer discrete components. They all can be integrated into a chip. This is a reflective electro-absorptive modulator integrated with SOA. So this has that semiconductor optical amplifier. So you have the seed light, that is a continuous light, and it travels. And this is a high reflection coating. So it gets reflected from here, and then this RF actually synthesizes the signal, and then you get your modulated signal. And associated with this will be some sort of noise also, which is called as ASC, which one has to, you know, you can't remove it because it falls in the same band as the transmitted signal. So, but it will destroy your optical OSNR or optical signal to noise ratio. So this is issue with such devices. There is some sort of ASC generated one, which one has to consider while doing the performance analysis. And in between, you use the SOA, semiconductor optical amplifier, which will amplify your signal. So this is a very standard product used in WDM also, but being used in TWDM also. That is the hybrid TWDM. It is what is REAM SOA. REAM is reflective, R is reflective, electro-absorptive modulator, which has semiconductor optical amplifier on REAM SOA. This is regarding tunable receiver. So tunable receiver is actually, there are 4 types. For example, this is an example of a 4 wavelength thermally 4-channel thermally tunable receiver. So basically, you heat the components, and then accordingly you change the characteristic, and that particular lambda 1 is sensed by that photodiode. So both the center wavelength and the channel spacing can be thermally tuned. And if you reduce the channel spacing from 200 to 100 gigahertz, the crosstalk will increase, and it becomes actually double. So such devices can be used if the channel spacing is, you know, more than 100 gigahertz, because otherwise the crosstalk element comes into play, and there's a lot of crosstalk involved if the channel spacing is made narrower. And as you see, you are able to separate out the different wavelengths here, and there is hardly any ripple coming from here. So 0.5 dB of that order ripple is present. So these devices, they have been realized. So this is a tunable receiver sample. So in TWDM, these were the devices. So I told you about the devices, but in TWDM, you have some nonlinear effects because there are more wavelengths. The power level is also high. I mean, power is of the order of dBm only, plus 5 dBm or plus 10 dBm, but it falls onto a fiber which has a very small cross section. So if you see, the power per unit area is quite high. So some of the non-linear effects will also play in. So your TWDM system has to be analyzed under these conditions to get the exact performance of the system. So nonlinear effects are basically divided into some scattering processes and parametric processes. Just a brief about scattering. There are two types of scattering which are there. Raman scattering, which is called as the stimulated Raman scattering, SRS, or stimulated Milan scattering, SBS. And parametric processes, they are four-way mixing or self-phase modulation or cross-phase modulation. So this SBS and SRS, these scattering processes, they are result of scattering of intensity-dependent attenuation constant. The attenuation actually depends on the intensity. So because of the scattering, the attenuation may be high. So this will result into some SRS and SBS. Whereas the parametric processes, four-way mixing or self-phase modulation or cross-phase modulation, they actually the intensity changes the refractive index of the optical fiber, and accordingly there will be some phase change. And when there is a phase change, there will be change in the optical intensity, which will actually result in some sort of non-linearity because of these effects. So all these effects have to be considered while evaluating a TWDM system. So this is a brief. This is just a slide for stimulated Raman scattering. So what happens here is actually interaction of light with vibration modes of the silica modules. And what happens during this interaction of SRS, the power is transferred from lower wavelength channel to higher wavelength channel. So if you have lambda 1 to lambda 8, because of this RS, lambda 1 power will get transferred to lambda 8. This is a typical gain which happens for the transfer. So this is Raman gain on the y-axis, and then you have the frequency shift. So that shift happens, and then there's a power transfer, and this shows that that power transfer is maximum at 13 terahertz, or you see a peak here. So this is going to affect your performance. Similarly, SBS, this is not the, like in this case, there is vibrational modes of the silica. Here it is actually acoustic waves which interact with the photons and results into SBS, a stimulated Milan scattering. And it results into some the scattering is in the backward direction. So this will actually interfere with the forward propagating light, and which will deplete the signal power. So as you see, this is a scattered power here, and this is output power. So as I increase the injected power, the output power normally should increase, but because of this SBS and the scattering happening, the increase is up to some injected power. After that, it becomes sort of flat. So there is no increase in output power. So you have to keep your injected power below this threshold. Otherwise, non-linearity will set in, and there will be degradation in the performance. So the effect of SBS or signal power is shown here, and the signal power reaches a constant or plateau once the SBS threshold is achieved, which is somewhere here. The other thing is self-modulation. So self-modulation is actually the refractive index depends on the electric field or in intensity in some way. of the light, which is given as N0 plus N2 plus I. And because of this nonlinearity, if you have a launch a pulse like this is the input pulse, the output pulse gets broadened because of self-phase modulation. So this happens in addition to chromatic dispersion, which happens. So because of this issue that the refractive index is function of the intensity of the light or the electric field which is impinging on the optical fiber, there is some sort of dispersion. Also, you see some ripples here at the output, which is called as self-phase modulation. Again, this is an important parameter which should be considered. The parameter is four-wave mixing. Four-wave mixing because in TWDM I'm using either 4 wavelengths or 8 wavelengths. So when they travel inside the optical fiber, they generate some new harmonics, and those harmonics could be different wavelengths. So some of the wavelengths will not fall in the band of where we have the signals, but some combinations may fall in those bands, and these are actually sort of noise, and they are called as four-wave mixing. And this element is quite high if you have very closely spaced channels, and if you have more power than more FM, and if your fiber has less dispersion. So this is a problem if you have a less dispersion, because more signals have more time to travel in phase, and thereby creating more FWM components. So this FWM or four-way mixing depends on how your channels are spaced, what is the input power, and what is the dispersion of the fiber. So these all have some bearing on the four-way mixing. The another is cross-phase modulation. So when you have more multiple wavelengths, so the channels are vulnerable to cross-phase modulation, because what happens, one optical channel causes changes in the refractive index, it will affect the other optical channels. So this will result into some cross-phase modulation. Again, this should be considered. This is an important parameter, should be considered while calculating the performance of a TWDM-PON. So this is a comparison between SPM, XPM, and four-way mixing, cross-phase modulation, and self-phase modulation. So these two are dependent on bit rate. FWM does not depend on the bit rate; it depends on the frequency, on the wavelength. The origin for all the impairments, the origin comes from nonlinear separability. That is, the refractive index is function of intensity, and there is a effect of this nonlinear. In SPM is phase shift due to pulse, phase shift due to co-propagating signals, and new waves. As I told you, the harmonics are generated, and they result into some symmetrical broadening of pulses. In XPM, may not be symmetric. In FWM, actually, you have more number of harmonics. So the shape of broadening or spectral dispersion does not arise. Channel spacing has no effect on SPM, but it has effect on XPM, that is cross-phase modulation and four-way mixing. So when you evaluate any system, basically these are the three parameters one has to calculate. At least these three parameters should be calculated in presence of nonlinear effects and other noise and everything. So one other important thing is Q parameter. M1 is level of one, optical 1 level, M0 is optical 0 level, and the noise contained in optical 1 level and optical 0 is denoted by sigma 1 and sigma 0. So Q is broadly defined as M1 minus M0 divided by sigma 1 plus C0. And once you know the Q for a OZ or on-off keying, you can calculate NRZ, you can calculate the bit error rate, which is given by half error function complementary Q by root 2. And also, a lot of information is available by looking at the eye or eye pattern at the output. I'll show you some of the eye pattern here. And there is one important parameter which is called as eye height. It tells you at what point you should sample the signal so that your probability of error is low. So eye height is given by this formula. So I'm not going to details how we arrived this formula, but these are, some simple formulas which one can use for calculating or doing the performance analysis of a TWDM system by calculating Q, bit error rate, and height, I height. So this is, there are many architectures of TWDM-PON. I mean, can coexist with legacy PON. So for example, this is your legacy PON, will be a 10 gigabit. And whereas these are your TWDM PONs. So these can coexist here in the same architecture. They are not backward compatible, but these two technologies, these two different technologies, TWDM PON and normal PON, can coexist. And this, for that coexist, for handling this inter-PON connectivity, you have to use some sort of elements, and which have to be compensated by this particular element, that is coexistence element. This is called CE, coexistence element. So specifications for this coexistence element is also defined. So this is one of the architecture where next generation PON 2 or TWDM PON can coexist with the legacy PON. So you don't have to remove all your existing equipments which are deployed in the network, but if you want to deploy TWDM, these two systems can coexist. This is how a TWDM can coexist with point-to-point WDM systems. So these are TWDM here, which you see here, which are multiplexed, and these are point-to-point. So you use another level of multiplexing here, then they're further multiplexed. So the whole thing has two levels of optical multiplexing, one for the TWDM, one for the point-to-point, and then multiplex and then transmit. And then similarly on the other side, you have TWDM PON ONU and point-to-point ONU. So again, this is another configuration you can use along with TWDM, where you can have some sort of point-to-point WDM or typically WDM coexist with a TWDM. So TWDM, there's a possibility, or there is a possibility of both point-to-point WDM as well as conventional PON to coexist. Typical TWDM network PON will look like something like this. You have PON OLT, this I have explained. So there are 4 wavelengths, they're multiplexed, and then 4 wavelengths go, they're split it up, and then you have the ONU, and then each lambda 1 is actually a TDM PON in itself. And these are optical network transmitter. I mean, this is slightly detailed about optical network transceivers. What are the different components in TWDM PON ONU, for example? So you have laser driver, DMB laser, ZM modulator. So all these devices can be integrated or can be used separately. And this is the wavelength plan for next generation. So I missed out about the wavelength plan earlier, but these are other technologies, EPONs or normal PONs or GPONs and all that. But this TWDM PON or next generation PON falls in this range. This yellow is for upstream, and this yellow is for the downstream. So all your lambdas for the upstream have to be in this wavelength, and downstream have to be in this wavelength, which is actually a part of C band here and part of L band. So it has both C and L band wavelength for next generation PONs. These are some specific wavelengths which I have shown in red colors for a 4 wavelength TWDM PON. And first thing you have to do is you have to see whether your power budget is meeting or not. So this is a physical layer requirement. So basically you have to look for all the elements which are there in the network, which contribute to loss, like length of the fiber, or how many splices are there, or how many connectors are there. Then there is a separate element here, which is called as coexistence element. If you have conventional PON also part of the system, then you have to take care of this loss also. There's some splitter losses and all that. So you have to ensure that you meet the power budget. Your transmitter power is such and receiver power is such that you are able to meet the power budget. So the system this I just show you some of the results of system performance of a TWDM system, and I have assumed here the channel spacing is 100 gigahertz, and this has been analyzed based on if chromatic dispersion was the only culprit, or SRS or SPM, or you have a combination of SPM and XPM, or extinction ratio of the Mach Zehnder modulator, thermal and short noise. So I'll quickly go through some of the results. So this particular tells you the distance versus the penalty. When I say penalty means, I have to give that much of extra power in order to handle that particular impairment. So for example, suppose I want to cover a 40 dB distance and only chromatic dispersion or CD is the culprit, then in order to get this 40 kilometer, I need at least 0.4 dB of extra power so that I'm able to handle that CD impairment. So this is what I mean by penalty. This is in terms of dB. So these are, different curves for different kind of nonlinear effects. For example, this is SPM, that is self-phase modulation chromatic dispersion, when the transmit power is 3 dBm, when the transmit power is 5 dBm, when the transmit power is 7 dBm, 9 dBm. I mean, this basically tells you the effect of CD and SPM at different transmit power levels. So if you see the best is this one, that is CB plus SPM when the transmit power is high. So it so happens here that whatever dispersion or whatever penalty CD is creating, it is sort of getting compensated by SPM at high level. So in a way, this SPM is helping us in reducing the penalty. So if you want to handle only the SPM part, then you have to transmit, high power. Then you will be able to handle this SPM in a much better way. The penalty is much, much less. But if you have only the CD, then the penalty is quite high. So as SPM plays or is also counted in, there is an improvement, and it goes on improving as the input power increases. This is rather an interesting result here. This is the effect of thermal noise, different type of thermal noise on the receipt power and the BER. So if there is a high amount of thermal noise, there is deterioration in the BER, which is actually clear from this curve. So these are the different values of thermal noise considered in the simulation, and this is the receipt power, and this gives you the bit error rate. So for example, suppose you want to see at -3 bit error rate, and the receipt power is -33. If this is a thermal noise. So depending upon thermal noise, you get the receipt power, and then your receipt power will define what kind of signal to noise ratio you will get at the receiver. This tells you about the extinction ratio at the Mach Zehnder. Extinction ratio is actually power level at 1 divided by power level at 0. So if you take 10 log of this, it gives you some extinction ratio in 10 dB. And if the extinction ratio is high, that means if the power level at 1 and power level at 0 is high, then it is less susceptible to noise, and you will get the improvement in the performance if the extinction ratio is high. So which is very evident from this. I mean, this is an eye diagram shown here. The eye opening is very clear here, whereas the eye opening is bad, or eye opening height, in other words, is good for a system where the extinction ratio is high, that is 15 dB, and which is obvious. This is channel spacing tolerance. Channel spacing tolerance is basically tells you what is the channel spacing and what penalty you will get if the channel spacing is brought close to each other. So for example, if the channel spacing is the order of 15, less than sort of 15 gigahertz, then the penalty is huge. And more than 20 or 25 between two adjacent channels, gigahertz, the penalty because of this channel spacing is very, very low. And this, I will not go into the detail of this, but basically this curve is telling the different effects of impairments or nonlinear impairments, whether it is a combination of chromatic dispersion, self-phase modulation, nonlinear effects. This is Raman, different powers. You can give, different powers to different channels, and then you can see what is the Raman effect. This is, cross-phase modulation and self-phase modulation. This is Raman with equal power, Raman with equal power. So these are various combinations which have been studied, and the plot between distance and BR has been achieved. Our objective is to get, 10⁻⁻3, and accordingly you will get the distances if you consider, these kind of nonlinear effects. And this is a corresponding curve which gives you the penalty. That is, in order to meet, in order to compensate for these impairments coming as a result of self-phase modulation, cross-phase modulation, or Raman scattering effect, or SBS and all that, how much extra power you require at the transmitter, or what is, in terms of sensitivity, what is the improvement you require at the receiver in order to cancel out these effects and get some performance level of your choice or desire. And these are, the spectrum of these 4 wavelengths of the TWDM. And this is the I, for example, this is after cross-phase modulation. This is adding some other, impairments, this is another impairment. So by looking at the I or calculating the I height, you can find out the deterioration in the received signal. This is crosstalk. Let me escape. So just a few, I think. Amit, can I take 5 more minutes?
Yes, sir. Sure, sir.
Okay. So I just try to wind and then I'll take questions. So now the latest trend is that TWDM-PON, standards are working on 50 gigabits per channel. Earlier was, 10 gigabits per channel. This is 15 gigabits per channel. So if I have a 8 wavelength PON and 50 gigabits per second per channel, then the total capacity of that PON is going to be 50 to 8. That is 400 gigabits per second. So this is what the standard bodies are working on. That is the next level of PON, which is called as high-speed PON or HS PON. So HS PON, and why this requirement has come, because I need, at least a gigabit of service available to me, and that system should be able to cater to 64 ONUs because of advanced services which are bandwidth hungry services like virtual reality or augmented reality, which are becoming popular in residential markets. So I require at least 1 or more than 1 gigabit in my desktop. So there, this gigabit PON will play an important role. This is a 50 gigabit PON architecture. Again, I will not go into the details. This is how a receiver will look like. It will require, not pin diode, but some APD, avalanche photodiode, and some sort of, TIA, so transient impedance amplifier. So the receiver becomes really complicated if you're handling, 50 gigabits per signal. And you also require very sophisticated forward error correction techniques, which will require both, could be hard decision or soft decisions, and very advanced codes like LDPC codes or concatenated codes, combination of, Reed-Solomon or BCH. These advanced type of codes are required to get a coding gain. So these 2 graphs actually tells you the coding gain you will get as a result of this coding for soft decision and hard decision. This is for soft decision, this is for hard decision, and these are some of the codes which are likely to be used in 5G PON, 50G PON. I think this radio on fiber I will skip in the interest of time. So there were some results on radio. Just I'll tell you why I was considering this. Now, this is again another hybrid architecture wherein the output coming from a mobile, which is actually analog in nature, carrying at some carrier frequency, they are getting terminated an OLT, and this radio signal, which is coming from mobile network, goes through the optical network and then goes to a BTS, and then there is a distribution, or it can go to a fixed wireless, or it can go to AONU. So all three possibilities are there. You can connect to a fixed wireless, or you can connect to a BTS tower, or your standard conventional ONU. So this is called as radio on fiber. This is again becoming popular, and a lot of research happening in this area because sending.
Sir, I think your voice is not coming. Other participants listening the voice.
Yes, sir. Sir is audible.
Okay.
Yes, sir, audible.
Yeah, I think Amit, there was some problem.
There might be some problem in my side.
So, yeah, but I can hear you. Yeah. So just to conclude, this is radio on fiber. There are some results. So in the interest of time, I will not discuss, but at least one result I will explain you here. This one. So this is actually the wavelength versus bit error rate. And for radio on fiber, if I consider only cell phase modulation, this is the kind of result I get with respect to BR. If I consider the green one is cross phase, then this is the curve. And if I consider four-way mixing effect, this is the curve. So what it shows that four-way mixing is very detrimental for such kind of fibers, ROF or radio on fiber among these three. But ultimately, one has to evaluate all these impairments and see what is overall performance. But individually, if you do, then four-way mixing is more detrimental as compared to other nonlinear effects. This is Raman results. So what is the challenge? Hybrid PON challenge. Now, the objective is to increase the capacity, and the capacity normally we use NRZ on-off keying. But if you use high modulation, next level of modulation techniques, that is dual polarization MCOM, or this is DP, dual polarization and QPSK. Yeah, this is my last slide. I'm in the box. No, I'm not able to hear you, but I don't know other participants are able to hear me or not.
I think I need to.
Hello,
Yes, Anand sir. Yes, yes, Anand sir, you are audible. Yes, Anand sir, you are audible.
Yeah, Amit, I think there's problem at your end. Other participants are able to hear.
Sir, not audible for me. Last 2 to 3 minutes, not audible.
In 2 to 3 minutes, Amit Garg or Mike? Anyway, let me have my final slide. You are able to.
Hello.
No, so I just once again I want to ask the participants if I am audible. Then I'll repeat my last slide.
Yes, Anand sir, you
Yes,
are
sir,
audible.
audible, sir.
You are
Yes,
audible,
sir, you
sir.
are audible.
Okay, Amit, I think there's a problem with you. So I'll just continue my last slide, and then maybe you can log in once again if see it improves. So the challenge with hybrid PON is you want to increase the capacity, and by using high modulation, that is a one-way forward. This is what FSAN is working on. And how do you mitigate? Okay. Yeah. So how do you mitigate nonlinear effects? So there are some techniques, use digital signal processing. This is how you can compensate your NLE, nonlinear effects. How do you extend the reach, long reach using hybrid PONs? And power consumption is also very, very important, which I have not discussed in this presentation. So how do you make your ONU sleep or go to dosing mode or some power shedding mode so that the power consumption from the ONU is reduced? So there are again a lot of work going on in these areas. What is the protection mechanism. If link fails or ONU fails or the feeder fiber fails, how do you protect your subscribers or your users? So again, I have not covered here PON protection mechanisms for hybrid PONs. Security, how do you ensure that whatever you're transmitting is secured? So this is another area which is open for discussion, and standard bodies are debating on that. And PON monitoring. PON monitoring, suppose the fiber is broken, so immediately, you should be known to the operator so that, some immediate action can be taken. And you should be able to monitor the whole network. So these are the areas where still a lot of work is going on, which actually I have not discussed. Mostly I was concentrating on how to handle the nonlinear effects, or the effect of nonlinear effects, or what is the capacity.
Excuse me, sir. Your voice is not there. Your mic is muted, I think. Excuse me, sir. Your mic is muted, Anand sir.
Hello. Yes, now am I audible? Yes. Anand sir, you might.
No, well, I don't know how it happened, but
now it's
my last slide.
fine,
Yes. Okay. So I think I missed out the last slide. So these are some areas which I have not touched about: power saving, PON protection, PON security, PON monitoring. But I think I was able to do some justice to hybrid PON. Is a new class of PON which has both TDM and WDM components, wherein we have discussed what is the kind of speed we get, and what is the reach we get, how the performance is affected by nonlinear effects, and what are the different architectures for deployment of hybrid PONs, whether it can coexist with point-to-point WDM or conventional GPON. So these things we have discussed. So I hope this will generate some sort of interest in audience, and probably they will do some more work in these areas. So thank you very much for listening to me, and now I'm open to any question or any clarification from the audience.
Oh, good morning, sir.
Good morning.
So my question is, how less dispersion causes more FWM components?
Yes, your question is very interesting. So first of all, let us understand how four-wave mixing is caused. See, when two waves which are having same wavelength or very close wavelength, they travel, so they interact with each other, and they interact more with each other. So what happens in a fiber which has very low dispersion, or say zero dispersion, these waves for a long time will travel very close to each other. So there will be a lot of interaction which will happen between these waves, and once they get enough time to interact, they will generate these harmonics, and there will be more number of harmonic components. If the dispersion is high, so they have very less time, or the interaction between these two wavelengths is much less. That is why less four-wave mixing components or reduced four-wave mixing components are produced. So that is why when the dispersion is low, the four-wave mixing effect is high. That is why in telecom network, you have non-zero dispersion shifted fiber, NZDSF, because deliberately you have non-zero dispersion, so that once you have WDM or DWDM in optical fibers, the four-wave mixing effects are less. So that is the reason of having zero dispersion and some finite dispersion, so that your FWM components are less. Is that okay?
Yes, sir. Thank you.
Yeah.
Yes, good morning, sir. Myself Jayesh
Yes,
Prajapati.
any other question?
Sir, yes, sir. Myself Jayesh Prajapati. Anand, sir, good morning.
Good morning.
Yes, sir. While talking about that hybrid PON structure, sir, you were just talking about the coexisting element. Actually,
Yes.
what is that thing? And you have said that some of the parameters for which we have to take care. So please, can you
Yes.
put some light on that thing?
Yeah. So coexisting, as the name suggests, you have a normal TWDM network, and you have other applications, GPON also. And this GPON can be either a TDM PON or it can be a point-to-point WDM PON. Now, when you are connecting this TWDM PON with a different, PON, again TDM or WDM, and they have to be multiplexed. Now they may be coming at some wavelength; these are coming at some wavelength. So you need a special equipment which actually will multiplex these different types of PONs. And this element is nothing but actually a WDM multiplexer. So the moment you use a WDM multiplexer, there will be some insertion loss. So that insertion loss of that device has to be taken care of when you are planning the overall budget. So when you have different class of equipments getting in the network or coexistence in the network, this extra element has to be put, which is actually a coexistence element, which is nothing but a WDM. And this ITU has given a parameter that you can't have more than 1.5 dB loss. I think there is some such figure. So this is what this coexistence element means, CEX. Is that okay?
Yes, sir. Yes, sir. Thank you. Thank you very much, sir.
Okay.
And sir, one more small question is there.
Yes.
Sir, as you have mentioned that to deal with the nonlinear effects and all, ultimately, is it the only one thing that we must have to use the DSP algorithms and all that thing? Or is there any other way, like with use of higher order modulation schemes, like 3264 QAM and all, and along with OFDM, can we do some work? So whether it will give some better result, or DSP is the only one option for that?
I mean, DSP is one. Other option can be, you can have mixed line rate. Mixed line rate may give you less, nonlinear effect. It's like when I say, you can have 10 gigabit or 2.5 gigabit, different types of giga rate, or the spacing can be not uniform. I mean, if wavelength we use may not be a uniform spacing.
Yes,
So,
sir.
and when you are using some amplifiers in between, so there are many places, common amplifier, then you can have load amplifier, or you can have some other type of amplifier. So again, depending on the amplifier, you can reduce some of these effects. So these are some additional areas which one can look into to reduce the nonlinear effects. ESP is one of them. And OFDM, high modulation things, it's actually a next level of PON people have not considered so far. Maybe another area is what which can reduce non. Yes, that is one of the options. But these are the other options which I have mentioned.
Yes, thank you very much, sir.
Okay.
Yes, any more questions from participants?
Sir,
sir.
good morning, sir. Bhaskaran.
Yeah, please go ahead,
Yes.
Bhaskar.
Yes, sir. The combination of this self produces this special kind of waves that is known as soliton pulses.
Yeah. So that is yeah, that is why I said, when you have self-phase modulation, because if you have only chromatic dispersion, your chromatic dispersion will be very high, after say 40 or 50 kilometers. But once you have SPM, self-phase modulation, it has a negative effect. So, this is the principle of soliton pulses, that the combination of CD and SPM, soliton pulses. So it gives you some narrow pulses. So this is what, I was able to show in that graph, that, combination of SPM and CD at high power, actually you get very good results. So because you are going to a solid-on regime, so this is what what is happening here. Is that the question, or is there anything else?
Yes, sir. Yes, sir.
Yeah.
So, sir, can we say that like FWM is just trying to, it may even what you can say, introduce the TDM third order distortion or something like that? For that also we have to take care.
I mean, third order will also give you some impairment. I mean, you can analyze and see what is the effect the third order gives, but significant impairment comes from the second order. Third order will affect, but the contribution may not be that high. But one can expect to see whether what is the in terms of value, how much degradation happens if you consider the third order effect.
Yes, sir. And sir, sorry for one. There is one last question that I would like to ask, and that may be, I think, question of many of us. Sir, yesterday we were discussing with one of the other faculty. Like, sir, whenever we are just doing such work in a simulative domain, like using some software and all that thing. So while working with BER values and all that thing. So, sir, sometimes Q value, it indicates too much high, or even particularly for BER, because that simulative result shows something like 10 raised to minus 90, 10 raised to minus 100 and all. I think it is not the practical thing. So please, can you, sir, just mention some ideal range, because when we are working such simulative work and all, so what should be our optimum range for which we have just tried to optimize that system?
I mean, yes, simulation results actually will give you sometimes very good results, which will not happen in practice, because in practice there are a lot of other things. And when you are doing simulation, I mean, you are modeling these things, how these impairments are going to interplay and all that is very, very difficult to say. So simulation will at best give you some indication what kind of performance you're likely to get in the field. But the simulation results and the field results and the analytical results, all three, will be different. And ultimately, it is a field result which actually. So simulation has, its limitations. You may get good result. You may declare that you have good result. That is why, most of the papers which get accepted, your simulation work should be supported by some experimental results, and there should be some close agreement between the two, so that your simulation model and actual model, they have some resemblance. So yeah, one has to be careful with the simulation results. So does that answer, or you were looking for something?
Yes, sir. Okay, thank you very much, sir. Thank you very much.
There is one question from also, sir. So in field, so basically for tunable FBG devices, so what kind of tuning is preferred, sir, practically? That is for changing the refractive index, or for stretching or relaxing kind of things. What kind of tuning should be preferred, or it is easy?
No, that depends on the application. If you are using it for TWDM, where you're going to be 4 wavelengths or 8 wavelengths maximum, probably a TFF kind of thing is much better. But if you are using those kind of device for, say, dense WDM or ultra dense WDM, where you have 32 or 64 wavelengths, then you require a different technology. So because, and also depends what is the spacing, what are the lambda 1, lambda 2, what is the spacing between the two. All these factors, the cost, all these factors will decide, or the application will decide which technology you have to use. I mean, there's no point in using a few nanometer tuning device for TWDM, where the difference between two wavelengths, lambda 1 and lambda 2, is of the order of, say, 10 nanometers. So it will be an overkill. So again, depending upon what is the application, you have to select your tuning device.
Okay, thank you, sir. So I think we have covered almost all the questions.
Okay, thank you.
So I would like to again thank you, Professor Anand Srivastav sir, for giving the real and practical issues on the TDM and WDM PON. Basically, these are the practical issues which the sir has covered in this slide. So thank you, sir, for giving us the great information and great talk. Once again, thank you, sir.
Thank you very much. And thank you very much, everybody, all the participants, and Dr. Amit.
Thank you, sir.
Okay, so I have a class now, so I will log out.
Yes, sir. Sure, sir. Sure. Thank you, sir.
Thank you.
And all the participants are requested to join the next session at 12:30, please. Yes. Thank you, sir.